So in this video, we're going to go ahead and start looking at electron configuration. And what do I mean by that? Electron configuration is where electrons reside within an atom. We have to be able to determine where the electrons reside. Are we talking about core electrons or valence electrons? And why? Why do we care? We're going to talk about that as well. As a general reminder, we're going to see it again. Our valence electrons are what are involved in bonding. Core electrons are closer to the nucleus. Valence electrons are the ones on the outside. We want to be able to describe where the electrons reside for any atom we look at. Or ion. We can also look at cations and anions. We're going to use the periodic table to identify the electron configuration. So go ahead and pull out your periodic table now. You should be able to identify the S, P, D, and F blocks. The S block starts with one S. The P block starts with 2P, the D block starts with 3D, and the F block starts with 4F. So S, P, D, and F are the order we're going to go, and it's 1, 2, 3, and 4. Beginning with the first period again is your horizontal row across. You're going to proceed across the table horizontally, counting the electrons in the S, P, D, and F blocks. Again, we're going to practice this a lot, but let's go ahead and actually look what these blocks are. So on your periodic table, get one you can write on, and I want you to outline your S, P, D, and F blocks. First up is your S block. Your S block is here, comprised of group 1 and group 2, or your alkaline metals, and your alkaline earth metals. Now, they're not metals, but residing right here is hydrogen, and for the purposes of electron configuration, helium is here. If we look, this is the n=1 energy shell, n=2, n=3, n=4, n=5, n=6, and n=7. No surprise, that matches to the value on the S block. So that's where those numbers are coming from. They're matching to what we call your energy levels, or what energy level are you up from the nucleus. Hydrogen and helium fit here. So this is helium, but for the purpose of electron configuration, it's in the S block. It's not actually in our P block. Next up is our P block. P block is found over here. And that's some of your metals, most of your non-metals are in your P block, exception to that would be hydrogen, helium, etc. Your P block is over there. In the middle of your periodic table is your D block. This is also known as your transition metals. And at the bottom of our table down here is our F block. Most often ignored, but it does exist. We do have to pay attention to it. And that's your lanthanide and actinide series. And notice what I was talking about with the numbers. S block starts at 1, P block starts at 2, D block starts at 3, and F block starts at 4. So, a couple of rules we have to follow before we can actually start filling these in. We have to follow the off-ball principle, the Pauli exclusion principle, and Hund's rule. The off-ball principle is what we call your building up principle. We fill lower energy levels to higher energy levels when filling electrons into the orbitals. Again, that is the off-ball principle. So we can do it through the method that I was talking about, doing the periodic table, or I will explain this method in just a second. We also have Pauli exclusion principle, Pauli exclusion principle, the easy way of saying it is that you can have a maximum of 2 electrons per orbital as long as they have opposite spin. The more correct way to say it is that no 2 electrons in an atom can have the same 4 quantum numbers. Students aren't real big fans of quantum numbers. I know we've already talked about them in the previous chapter in the Module 8 series, but we're going to start applying them more in this chapter, and hopefully they'll make a little more sense. But Pauli exclusion principle means this. When I'm filling electrons, they will fill opposite spin. Notice that this is what we call, I shouldn't do arrows, I'm sorry. This one here is what we call spin up. This one here is what we call spin down. You will see me write them as spin up versus spin down. But we find is that no 2 electrons in an atom can have the same 4 quantum numbers. These 2 electrons are both spin up. They do not have opposite spin. They would have the same quantum number. And Hund's rule. Parallel before paired is the easy way of saying it. The more difficult but more correct way of saying it is when filling degenerate orbitals. Degenerate just means they're equal in energy. Electrons occupy the orbitals singly, one at a time, with parallel spin before pairing up, which is the better way to say it. So again, I'm going to go back to Aufbau's principle in a second to show you how to construct that graph, but this is what I mean by Hund's rule. This is representing a p block. The p orbitals can hold 6 electrons total. There is 3 orbitals. Each orbital holds 2 electrons. I am trying to place 4 electrons. I am going to place 1, 2, 3, and then my 4th. I am not going to do this. Electrons do not want to pair up if they don't have to. Electrons are repelling one another. It's kind of like, you're filling up the seats on the school bus, and okay, maybe your best friend is there and you want to sit next to them, but most people are more likely to sit by themselves until they have to pair up. You want your own space. The electrons want their own space before they have to pair up. So Hund's rule tells us the electrons will fill the orbital parallel before paired. And again, degenerate orbitals just mean that they're equal in energy. We'll talk about this more as well, but the s orbitals have one orbital, so they hold 2 electrons. The p orbitals, 3 shapes, 6 electrons, because there's 3 orbitals. The d orbitals have 5 orbitals, 5 shapes, 10 electrons. Each orbital holds 2 electrons. And F has 7 different orbitals, so they hold up to 14 electrons. The last one is this building up principle. I'm going to show you how to do this off the periodic table as well, but you can also always construct this chart. The way this chart works is you've got n equals 1, n equals 2, n equals 3, all the way down, okay? On the table right now, the periodic table right now, we have 7 ground state levels. But let's recreate this chart exactly. We know that the orbitals are filled S, P, D, then F. So you do have to memorize this to do this, to recreate this chart. You do have to remember that it's S, then P, then D, then F. N equals 1 means I have one type of orbital, 1s. N equals 2 means I have 2 type of orbitals. I have to start over every time. So 2s and 2p. N equals 3 means 3 types of orbitals. I have to start over with s, 3s, 3p, 3d. 4 types of orbitals, 4s, 4p, 4d, 4f. 5s, 5p, 5d, 5f. Now I could go to 5g here, because at that point we're going to start following the alphabet, but I'm going to stop at f because I'm looking at ground state. 6s, 6p, 6d, 6f. 7s, 7p, 7d, 7f. 8s, 8p, 8d, and 8f. So we've recreated it. We put a few more in there, but they would fill out that way as well. There would be 6f here. It's just that we don't have any ground state electrons in the 6f yet, and that's why it's not listed here. But now what I'm going to do is I'm going to diagonally cut across this table. I'm going to say I'm going to fill in my 1s first. Then I'm going to keep going, fill in my 2s, 2p to 3s, 3p to 4s, 3d to 4p to 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, and so forth until I fill out the table. And so when this finishes, it continues on to the next line. It's showing you how the orbitals are actually filled. You are welcome to recreate this and do this on a test. I personally think it's easier just to use the periodic table to do it. But 1s always fills first, then 2s, 2p, 3s, 3p. Or sorry, 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, 4p, 5s, 4d, 5p, 6s, etc. Personally, again, I find it easier to do straight off the periodic table. Just kind of looking at that chart again, S, P, D, and F blocks, and then the filling. So what I mean by easier to do it off the table is if I just count through the table here and I look at filling in the electrons, I'm always going to start up here at the hydrogen. Okay, I always start at the first spot. 1 electron, 2 electrons. I go across the table. There's nothing else there. So now I'm going to go to the next row. 3 electrons, 4 electrons. I'm still in my S block. So notice this is one of my 1s that I filled. Now I'm filling my 2s. I'm going to go across the table and I hit my 2p block. 5 electrons, 6 electrons, 7 electrons, 8 electrons, 9 electrons, 10 electrons. I've run out of space. I continue back down on the next next line in the table. 11 electrons, 12 electrons. I cut across the table. I'm back into my p block. 13, 14, 15, 16, 17, and 18. No more there. Cut back down. 19 and 20 in my S's. Now I hit my D's. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now I'm back in my P's. So if you can remember what the electrons are called, it isn't that hard to do it this way per se. This is my 1s, my 2s, my 3s, my 4s, my 5s, 6s, and 7s. P's are pretty straightforward. They kind of follow the same exact pattern the S's. 2s goes to 2p, 3p, 4p, 5p, 6p, 7p. This element does now exist. The trick comes in the D's. It's 4s and 4p, but this is a 3d, 4d, 5d, 6d, and the F's. You have to remember 4f. The F's start here. They start in the middle here. After the 6s, it's 4f, 5f. So you got to be careful down here. We will practice this more, though. So some terms we have to know. Ground state and excited state. What do we mean by these? Ground state is just that. It's your lowest energy state. It's the electrons are in their most stable state. They don't have any extra energy. It's just where they're going to reside. The excited state is any state other than the ground state. I've given that atom some energy. The electrons are now excited up to a higher energy state. And so a photon of energy has gone in. We've learned about photons. H nu represents a photon. A photon has gone in, excited this electron to a higher energy state. Degenerate just means equal in energy. We have non-degenerate orbitals and degenerate orbitals. An s orbital is non-degenerate. S orbitals can only hold 2 electrons. Each orbital holds 2 electrons. S has 1 orbital shape. We learned about that in chapter 8. It's a sphere. P has 3 orbital shapes. So 3 orbitals, 3 shapes. This means S can hold 2 electrons, whereas P can hold up to 6 electrons. But the p orbitals, like here, are degenerate. It has 3 different shapes, 3 different orbitals, but they are degenerate orbitals. They are equivalent. Px, Py, and Pz are degenerate. My D's, D has 5 orbitals, 5 shapes, can hold up to 10 electrons because each orbital can hold 2 electrons. And then F has 7, so it can hold up to 14 electrons. We also have node. A node is a region in space with zero probability of finding that electron. It's where the electrons are not allowed to reside. So you can see here, s orbitals do not have a node. P orbitals have a node. D and F orbitals also have a node. A shell is your energy level, and that's your n equals 1, n equals 2, n equals 3, etc. And your subshell is your energy subshell. So the shell is your quantum number n, your subshell is your quantum number, your subshell is like which type of orbital do you have. So it's your L value, but with your shell, it will tell you which type you're in. So, do you have a 2p? Do you have a 2s? Are you in a 4d? Where are you at? Here we can kind of see it as well. We have the orbitals. Each one of these is an orbital, but a shell is the overall n equals 2 shell here. And the subshell here is 2s and then my 3 2p's. So again, looking at the periodic table, and how we're going to do this is I look at this as the guide to how to actually figure out my electron configuration. I know this is my S block. I know this is my P block. I know this is my D block. And I know this is my F block. So S, P, D, and F. And I know helium is hanging out right here. For any electron I'm looking at, I'm going to come across this table to figure out what its electron configuration is. So I'm going to kind of be flipping through the next slide and back to this to kind of show you guys how I do this. So give the 4 quantum numbers and electron configurations for the following species. All of these are neutral atoms. So let's look at hydrogen. I am always starting at this first spot. The number here is my N value. My L value. M sub L is which degenerate orbital. And M sub S is electron spin. So I'm looking at hydrogen first. I see hydrogen hanging out right here. So I've counted 1 electron over. I'm in the S block. I'm in my S block, and I'm in the first energy shell. So I've got 1 electron in the S block, and it's the first shell. Electron configuration here is going to be 1s1. The 1 here is my principal quantum number. The S is telling me the type of orbital. And this is telling me the number of electrons that species has. So N equals 1, S block, 1 electron is hydrogen. The electron configuration here is 1s1. My quantum numbers are N, L, M sub L, and M sub S. Now, N matches this first number here, 1. L tells me the type of orbital I have. If L is equal to 0, it's an S orbital. If L is equal to 1, it's a P orbital. If L is equal to 2, it's a D orbital. If L is equal to 3, it's an F orbital. It is an S orbital, so my L value will be 0. And M sub L is equal to negative L through 0 to positive L. The L value here is just 0, so M sub L is only 0 as well. All that means is that if I had different types of orbitals, I'd be able to describe which orbital I have. In the case of hydrogen, it only has an S orbital. There's only one shape. It's not degenerate, so the M sub L value will be 0. And when we're doing this, really what we're doing is we're filling in the electron in the 1s orbital for hydrogen. So this is looking at the energy scale. I have 1s electron, and I have 1 electron in it. We assume the first electron to go in is spin up, which would be positive 1/2. So we are assuming the first electron in for hydrogen is going to be a plus 1/2 spin. Let's look at helium. So we've looked at hydrogen, and we saw that, we had 1s the 1s1, helium is right next to the hydrogen. So I'm still in the n equals 1 energy level. I'm still in the s block, but now I have 2 electrons. Again, helium looks like it's above your p block. That is because it is a noble gas. For electron configuration, you need to put it on top of your alkaline earth metals. It is in the s block. It has 1s2 for its electron configuration. The principal quantum number here is still 1. I'm in the first energy level. My L value is 0 because I'm still in an s orbital. My m sub L, still 0 because I'm still in s orbital. And my m sub s is talking about that spin again. If I look at helium, looking at my energy scale, 1s, it has 1 and 2 electrons. So it has both of these. It has plus 1/2 and minus 1/2. So it will have 2 separate m sub s values, one to describe each electron. Notice when we say no two electrons can have the same principal quantum numbers, that's because these 2 electrons here, the 2 electrons for helium, differ in their m sub s values. They have the same n value, they have the same L value, they have the same m sub L value, they differ on their m sub s. One is plus 1/2, one is minus 1/2 for spin up versus spin down. Okay, now let's look at lithium. Back to our table, we go across, there's nothing else here in the table. There's no p block over here. So now I'm down to the n equals 2 level, and I see lithium here. Lithium is in my second energy level, and it's still in the s block. I'm going to write this over here and then copy it over because it's really hard to write on the bottom of the screen. So I've got 2s. Oh, sorry, I got to talk about all electrons. I forgot, I'm not just doing shorthand here. We will talk about a shorthand configuration. If I want to talk about all the electrons lithium has, it is all the electrons that helium has, plus 1 more electron in the 2s block. So it has 1 and 2, like hydrogen helium had. It has the same electrons as helium, but it has 1 more for lithium. So I'm going to say 1s2 for the 1 and 2 electrons there, and then 2s2 or 2s1 for the 1 electron in the 2s block. So lithium, 1s2, 2s1. Now for the quantum numbers, I'm only going to describe the last electron added just because it's going to get messy otherwise. If I want to look at the last electron added, that's the electron here. Principal quantum number is 2. My L is still 0. I'm still in the s block. M sub L, still 0. I'm still in the s block. And my m sub s, now this is looking at lithium. Lithium has 1s, 2 electrons, and 2s, 1 electron. We're talking about this electron right here. So plus 1/2 for the m sub s value. Let's look at beryllium. Let's clean this up just a little bit. If I look at beryllium, 1s1, 1s2, 2s1, 2s2. I've now hit beryllium. So 1s2, 2s2. Now for the quantum numbers, sometimes it's easier to see it by looking at your atomic orbitals. What I'm drawing here, by the way, is atomic orbitals. It's showing how the electrons are distributed. So 1s2, 2s2. I want to take the quantum number of the last electron added, which is this one here. We always assume, just by convention, the first electron added in is spin up, the second electron added in is spin down. Principal quantum number here is 2, because it's in the second energy level. The L value here is 0, because I'm in s orbital. The m sub L value, 0, because I'm in s orbital. And the m sub s value here is minus 1/2, because that electron is spin down. Let's look at boron. Now we are over here. So we've got 1s1, 1s2, 2s1, 2s2. We travel across the table. We're now in the p block. This is 2p, 2p1. 1s2, 2s2, 2p1. If I look at the atomic orbitals for boron, again, it's just showing your energy scale. 1s is lower in energy than 2s, is lower energy than 2p. Now the p's, I have 3 degenerate orbitals, px, py, pz. Each orbital holds 2 electrons. If you ever forget that, if you count across, 1, 2, 1 orbital. 1, 2, 3, 4, 5, 6, 3 orbitals. It's always half of how many you can take. This can hold, this is held in 1 orbital. Theoretically, 1 orbital, 1 orbital, 1 orbital. They don't feel like that, but it's how you can think about it. Each orbital can hold 2 electrons. The D's, if you ever, 1, 2, 3, 4, 5. Again, they do not feel like that, so please do not feel them like that. But if you ever get confused, that's one way to do it. Or count across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 divided by 2. 2 electrons per orbital, 5 orbitals. So my P's, I do have to draw 3 of them, but I only have 1 electron in them, 2p1. So I'm trying to describe this electron here. N equals 2. L equals 1 because I'm in the p block now. Now my m sub L is going to matter. My m sub L can be -1, 0, or +1. By convention, the way we're going to do this, let me move this down a little bit, we're going to assign the first one a -1, the second one a 0, and the third one a +1. It's just the convention we're going to follow. It is arbitrary, okay? We're assigning it -1 to 0 to +1. So the m sub L value here would be -1. The electron is spin up, so the m sub S value is +1/2. And I'm going to do copper near the top of the screen here and then move it down. Or sorry, I always say copper, I meant carbon. Carbon at the top of the screen here. Go back up. If we look at carbon, 1s1, 1s2. Haven't hit carbon yet. Keep counting. Oops, I'm flipping too fast. 2s1, 2s2 have not hit carbon yet. Keep counting. 2p1, 2p2. We've hit carbon. So again, if I looked at the atomic orbitals here, 1s, 2s, and 2p, 1, 2, 1, 2, 1, and 2. I'm going to fill them degenerate. I'm going to fill the degenerate orbitals in parallel before I pair them up. They're not going to pair up until they have to. But I'm talking about this electron right here. My N value there is going to be equal to 2. I'm in the second energy level. My L value is equal to 1 because I'm in a p orbital. My m sub L, -1, 0, +1. Going to be equal to 0. And my m sub S is going to be equal to +1/2 because that electron is spin up. We will do more practice with this as well, but I want you guys to have a brief overview of it before you come to class. Put that there. Try to move you guys back down. And so these quantum numbers describe where that electron resides. If I told you the electron was N equals 2, L1, M sub L 0, M sub S +1/2, I should be able to tell you it's carbon. What do I mean by that? Let's do a different one really quick just to show you. It's not in your notes, I know, but like if I just gave you some random quantum number and said, here's what it is, what electron am I looking at? Let's say I said N equals 4, L equals 2, M sub L equals -1, M sub S equals +1/2. N equals 4 is fourth energy. That will either be, got to be careful on that, that could be something in here, something in here, something in here, or something in here. Why? Because this is 3D, this is 4D, this is 4F, 4S, and 4P. So I know I've narrowed it down to there. Telling me L equals 2 tells me it's the D block. So I know it's not here. I know it's not here, and I know it's not here. I know it's one of these elements here. M sub L equals -1. The D block has 5 orbitals. L value of 2, which means it goes -2, -1, 0, +1, +2. So this would be -2. This would be trying to draw this thick enough. This would be a -2 value. This would be a -1, 0, +1, +2. -2, -1, 0, +1, +2. I've now narrowed it down to one of 2 elements. Last thing I have is M sub S plus 1/2. That means the first electron added in, which means it is not that, and we have identified zirconium. So we can use those quantum numbers to identify exact electron we were talking about on this table. Here's a nice diagram from your book actually showing how these things are just filled. This is, again, the same thing periodic table is doing. We fill your 1s electrons first, and we can fill 2 electrons per orbital. So 1s fills, then 2s, then 2p, parallel before paired, 3s, 3p, parallel before paired. Notice I'm putting the first electrons in, spin up, the second electrons in, spin down. 4s, then 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 4p, 1, 2, 3, 4, 5, 6, to 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6t, and so forth. If you follow through on the periodic table, you should be able to get the right configuration. Summary, the principal quantum number is your energy level. And the L value tells you the type of orbital, meaning S, P, D, or F. M sub L tells you the shape of the orbital, shape within the type. What I mean by that is because some of them don't always have the same shape, right? Shape, or maybe a better way to say it is orientation, because the type of orbital really does give you a shape as well. Orientation of orbital. So like PX versus PY versus PZ. And S is giving you your electron spin. Spin up or spin down. So, and N equals 1 only exists for the S orbitals. N equals 2, S orbital and P orbitals. N equals 3, S, P, and D. Once I get to N equals 4, S, P, D, and F. Within that, my L is telling me the type. Is it L equals 0? Is an S orbital. L equals 1 is a P orbital. L equals 2 is a D orbital, and L equals 3 is an F orbital. And then you've got 1, 3, 5, or 7. And within here, they're numbered 0, -1, 0, +1, -2, -1, 0, +1, +2, and -3, -2, -1, 0, +1, +2, and +3. Spin up is +1/2. Spin down is -1/2. We will practice a little bit more, but I need you guys to start seeing the correlations between your atomic orbitals and your electron configuration and your quantum numbers. So another periodic table, just so we can have it to reference back for the last 2 examples we're going to do in this module, which are here. Write the complete electron configuration of titanium and the complete electron configuration of iodine. Now, we will learn a shorthand configuration as well that we will do most of the time, but sometimes you are asked for the complete electron configuration, so you need to be able to do both. Let's go ahead and look at the table and find titanium. Titanium is Ti, and I always forget where the heck it's at. There it is, number 22. Should know that. I love one of my favorite numbers is 22, and I always forget where titanium is. I know it's metal, can never find it. But let's count. We know helium is actually residing right here for electron configuration specifically. So 1s1, 1s2. I have not yet reached it. 1s2. I'm going to write it down just so I don't forget. 2s1, 2s2. Still haven't reached titanium. 2s2. Now I'm going to go across the table because now the P block has shown up, right? There's nothing here because that helium is over there. So 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, but still no titanium. Front of the table, I go to the next row. 3s1, 3s2, no titanium. Across the table, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. I'm getting closer, but not quite there. 4s1, 4s2. Now I'm in the D block, and I have to remember that this is 3D. 3D1, 3D2. And I have reached titanium. If you ever want to check yourself, if you add up your superscripts here, 6 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 2 is 22. This represents 22 electrons. And when I look at titanium, its number of electrons is 22. So that's the perfect way to check to make sure you've done it correctly. Or I could just say, okay, I'm ending in the D block, the third energy level, second electron in. You know, I can find that as well. But complete electron configuration, you have to show where all the electrons reside. Clean this up so we can do our next example. Okay, it is iodine. So for iodine is one of my halogens. And it's down here at number 53. So I better be adding this up to get to 53 electrons. 1s1, 1s2. 2s1, 2s2. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. I'm going to go ahead and write those down. So I've hit 2s1, 1s1. This is why I like to write them down in pieces. 1s1, dang it, 1s2, 2s2, 2p6, because I forget the numbers otherwise. 2p6, 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Okay, so 3s2, 3p6. 4s1, 4s2. I'm about to enter the D block. I know that my D's start at 3. 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, and 3D10. Back to my P block. 4P1, 4P2, 4P3, 4P4, 4P5, 4P6. Five S1, 5s2. 4D1, 4D2, 4D3, 4D4, 4D5, 4D6, 4D7, 4D8, 4D9, and 4D10. We're very close to being done. And back in my P's, I'm in my 5th energy level, so 5p1, 5p2, 5p3, 5p4, and 5p5. And if I add up all my electrons, 2 plus 2 plus 6 is 10, plus 2 plus 6 plus 2 is 20, plus 10 is 30, plus 6 plus 2 is 38, plus 10 is 48, plus 5 is 53. I added them up correctly. So I have done my electron configuration correctly. Again, we're going to do more examples in the next module, but I want you guys to have a basis of it before we get to class.